do second part of that, automatic generation and control. In the earlier discussion, module number 1, unit commitment and concerned solution of problems with the priority listing, brute force method and dynamic programming method were interacted, and additional videos regarding solution of problem related to dynamic programming was enclosed in the earlier uploads in the MS Team, and you can find the support material from there. Then any queries regarding, I can help definitely. Again, from that, switching to the next module, automatic generation and control. It is another good aspect of power system operation and control, which we need to study from single generation aspect point of view, interconnected operation point of view, and further related to that. Let us begin under this heading, automatic generation and control. What are all the things we are supposed to understand one by one, and let us build the knowledge connected to individual generating point of view and another. And in line with this, I begin with the first interaction. What do you mean by automatic generation controller? What are all the objectives of this control loop or control mechanism? As you can see on the slide, there are 4 sub blocks I have mentioned in the right and in the left, like that. The first left top, you can see automatic generation control is a control that has 3 major objectives. Like you will find what was the objective of power system operation and control. It is to generate adequate megawatt and megavolt ampere reactive, deliver to the end user to meet their subjected specifications effectively, maintaining the voltage and frequency at steady state. It was the objective we defined for the power system operation and control. Then who will follow that? Who will work in line to reach those things? When I come down to a power system, to a energy control center, down to a generating station, down to a load center, etc. Who are all the players, stakeholders of that control? That comes, the first is generation aspect. When a power system is defining a certain objective, it should be fulfilled by the component interconnected inside which. That is, the automatic generation control is a computer control of generation and delivery of power to the load, in which this AGC, if I speak of, has objectives like it should maintain the frequency very close to the specified value, an example 60 Hz or 50 Hz in the continent. This content is taken from Wood and Uhlenberg presentation. Hence, it was an American content, 60 Hz was mentioned, and I will be preferring you people to refer it as 50 Hz. So, the first objective is to keep the frequency at specified value with the tolerances mentioned. Maintain the correct value of interchange power between control areas. It means, let us imagine you have a generating station under your view. There are 10 generators and you are generating a power, certain megawatt, and delivering it to the grid, and grid after being transmitted to the substation and later to the distribution point and to the end user, it is getting reached. Later, let us imagine you have excess power what you are delivering. That you are selling it to the neighbor power corporation for the trading of power. Then you have 2 objectives on the context. One is generate adequate megawatt of power to reach your local load or your control area's load, as well as meet to the commitment what you are doing. In that regard, it is to maintain the correct value of interchange power between control areas. Then the word control area is the area in which, to which the control signal reach and execute. Today we will learn what we mean by a control area, area control error, characteristics of control area error A, you will understand. With that requirement, the first keyword what we learned today is or undergoing is control area. Control area is the geographical periphery of a power system. It can be a power system, part of the power system, till that encompassing boundaries. Control signal from a center or from a common point execute, reach and act upon. That we call as a control area. Like that, generating station is a control area. Such another generating station is a control area. Generating station along with the load and transmission grid can be a control area. When control area is nothing but there is a central computing controller which signals the generator to generate a certain megawatt. That is called scheduling. Once there is a schedule, generator starts obtaining the megawatt and sending it to the grid, and from the grid it will reach to the end user. Therefore, when you shift that, the control enables in which route power has to be routed and how is that routing takes place. Then how is that received power and the sent power and the losses are computed and it ensures required megawatt being delivered to the end user, like that. That is a control area. From a control point, all those parameters were monitored and the balance among P and Q is tried to maintain. In that way, adequate value of megawatt has to be generated. Enforce contract for shipping or receiving power along the tie lines to neighboring utilities. This was the thing I was exactly discussing. Not only to maintain the adequate power generation, to see to that your local requirement you are able to fulfill, as well as your any contract selling of power, borrowing of power, if so for a certain hour of a day or a day of a month, something you have a contract, you will be able to manage that also. That comes under maintaining correct value of interchange power. Then the another important third objective, maintain each generating unit operating point at the most economic value. This is known as economic scheduling of generator because power system is a generation mix. Variety of generations are interconnected, hydro, thermal, oil or gas fired or renewable additional, etc. So those generations, according to their fuel cost functions, cost of production, incremental fuel cost of each unit, definitely ride on them. According to that and the changes that we find on the station, we call it a load duration curve. We should see to it that generation is adequate and able to meet that. In that due regard, so each generator has to be allocated with a certain megawatt for its cost effective operation because nature of the fuel, cost of the fuel, and once the fuel is burnt, its calorific value in terms of energy content available in that will diminish once it is being used and discharged. That has to be kept in mind, and overall the corporation has to see to it that its business will be in a progress. This is how the objectives are put into, that is the automatic generation control concept. You can just see this is a computer control of generation itself in simple view. Now I will move to the next slide. Most systems use automatic generation control to automatically change generation to keep their area control error close to zero. Area control error is nothing but an error stimulus for an energy control center where its set point we know what it is generating. Its demand we know what it has to meet. And any mismatch happening in between these two, that is called an error. That error has to be nullified, brought very close to zero, means what you are generating is actually meeting the requirement. Your system is under the steady. That's what is called area control. We'll see its magnified view in the upcoming slide. Area control error. Often controlled area has to be brought or maintained close to zero. That ensures steady state operation of the system. So it is possible only by automatic generation using computer controlled operation. Human cannot do it that easily because energy control center may be somewhere else situated. Resources are somewhere else scattered around the geography, and your command has to run from the energy control center to the generating aspect. There the correction takes place. Impact of that is on the load side. Again, accounting takes place in the energy control center. Corrections are again sent to the control. Like that, it is a closed system. Therefore, humanly it is not that easy to do. Otherwise, I can say impossible. So, automatic generation controller is just a computer-based development of megawatts and to deliver to the end user. And it should see to that when the steady state adequate megawatt, when I say adequacy is or net interchange is appropriate if its area error is close to zero. That's the meaning of the exchange of net power. Usually, the control center, either ISO or utility, independent system operator. We call it an independent system operator or a utility. Anybody who is connected to the power system. Calculate A, area control error. Present a transaction. Suppose a corporation A is having 5 generators. 5 generators are economically scheduled to a certain megawatt and it is pumping power to the grid. And it is maintaining the certain scheduled frequency. Power flow is occurring. Then, automatic generation controller concerned to that area refers to A. Do area control error of that station is 0? When it will be 0, what is that megawatt it is exchanging? All that calculation being done. Then to work towards maintaining the error of that station to 0, it will start accelerating the generation set point. Accelerating or controlling the flow into the turbine and managing the frequency and able to bring the steady state between that requirement and the generation. So it has to have a time slice base every 4 seconds. You can just see a simple example of American corporation. Generators are monitored their adequacy of set points in keeping the age of that station close to 0. Every 4 seconds, update of set point is done on the generator. This is how the dynamics at the controlling is being done. It is possible only by computer. Then, another aspect is automatic generation control implementation. How do you implement? So, automatic generation control schemes are usually centrally located at a control center. I was speaking about energy control center, wherein energy management software is installed. Some part of the generation aspects were assigned to a hierarchical control. Some part of the distribution activities are controlled by some other hierarchical controller. Then load side based and grid side based. All those activities were segregated on the priority and foreground computing, background computing, planning, analysis, assessment. All such functionalities are performed in the computer of a energy control center. There, automatic generation controller is also one of the computer programs which will be run to see to it that the computer which is able to develop the required content for that. Therefore, AGC schemes are usually centrally located at the control center. System measurements taken at major substations. The other information and data are telemetered to the control center. This was I was speaking. If we have an energy control center from the area wise locally, major stations where important locations of the grid, we call them as the buses. The measurement of suitable variable takes place. That measurement is through RTU, remote terminal unit, is transmitted to the master terminal unit located at the energy control center. That data is taken, processed in the control center. Like megawatt. unit megawatt power for each committed generator. Maybe one example, megawatt power flow over tie line to a neighboring system and the frequency of the system. Like an example, what are all your important parameters from a station you are required to process before you take or implement AGC in a computer center. That is like megawatt output of each generator, megawatt outflow to the grid and to the neighbor, and the frequency of the system has to be addressed. To address these things, it has to work in a computer algorithm and to develop touch point of the generator. Next is control actions are determined in digital sum. I was speaking very clearly. It is not that easy by a human being. The control actions were interdependent to so many aspects of operation. Hence, it is to be taken decision. A decision has to be taken so that what is the set point, what should be the control like that. So, it must be designed like an algorithm. They will run concurrent and in sequence depending upon your mechanism and need. They will develop an output in a digital computer. Then control signals are transmitted to the generation unit at remote generation station over the same communication channels. Like you can say, if I am using PLCC, power line carrier communication, same transmission lines I can use to communicate, or I can use satellite communication, I can use microwave communication, I can use PSTN, okay, public switch telephone network transmission line, or radio frequency transmission if the generators are very close to me. They were the channels to communicate from the energy control center to the generating station for the appropriate data to be transmitted, and its action on generator needs to be visualized. Therefore, it requires data communication to the end devices. Then, like an example, why you require data to be communicated from the master terminal unit, nothing but energy control center to the generating station. It is to rise or lower pulse signals to change a generating unit's load, reference point up or down, and suppose this is concerned to a transmission grid, transformers, the tap changing up or down like that, circuit breaker on or off you would like to exercise. They are the control signal. You will be deciding from the energy control center, from the AGC controller to act on those points of control for your suitable action. In this way, automatic generation controller is instituted in the energy control center to appropriately regulate the controlling of power generation and delivery to the requirement. Again, another view of which is automatic generator control implementation. The basic reset control loop for generating unit consists of an integrator. It's a clean case. So we will see how that integrates, because when I say automatic generation controller concerned to a generator, how do generator function? Generator is coupled to a turbine. Turbine in turn may be due to maybe a resource of hydro, thermal, or any other resources. That will be making the resource to drive the turbine, and turbine is coupled to the generator, and the generator in turn generates electrical power. How do you regulate the terminal voltage of the generator, and how do you manage the frequency of the output of the generator? They are the two important aspects: output power in terms of the frequency of its generated output and terminal voltage. So, if these three parameters, if I consider, there must be local control in and around the generator. I am concerned with generator now. In and around the generator, when I have a resource which is a hydro or a gas, whatever the kind of fuel, how do I regulate the fuel to the turbine, which in turn drive the generator at a certain RPM, so that generated power works with the required frequency F or 50 Hertz like that. So therefore, how do you regulate it? There should be a controller, and suddenly load is increasing. how would that change is reflected into the controller, so that controller reduce the valve or open the valve for the drop or rise in the frequency. So that has to be a closed loop here. That's correct. Integral controllers are used. We will see that also. How is that? Integral controller works for automatic load frequency controlling. Then I was speaking about how you maintain the terminal voltage of the generator constant. We call it as automatic voltage regulator. Automatic voltage regulator try to regulate the field input supply to the synchronous generator, monitor the input to the field coil, so that field poles are magnetized appropriately so that the developed voltage is at your required line voltage. We call it as automatic voltage regulation. So, automatic voltage regulation, automatic load frequency control are the two another loop, control loops to be implemented around the generator, which will have PI, proportional integral, PID, proportional integral and derivative controller, which in turn try to minimize the error and overshoot and stability of the control action associated with the generator changes. So this is at generator point. For this, the stimulus is controlled from AGC and the field local variable. So that's correct. Automatic generator control implementation is at the generator level to manage the scheduled power, and it has to function frequency deviation error to 0 and net exchange to unit value. So keeping the economy anchored. See, all the concerned parameters of definition of power system operation controllers are assigned hierarchically down the line distributed to the generator, load and other controls. As a broad, it is a responsibility of the power system. In turn, when you magnify the power system, there are so many integrated components, one to another interconnected. They are responsible for individual roles. Connected role is the role of the energy operation control. So this way, when it comes to a generator locally need to utilize the resource optimally. There should be a proper control loop to maintain the voltage, to maintain the frequency, even though there is a load or no load on the generator. This is how this generator side implementation for the automatic generation controller has to be there. Yes. This is the one of the slides already we have discussed. Why there should be a proper control in the power system? It must be able to supply actual required power supply to the every customer demand. Their specification must be met. It should meet the customer requirement at all the times, reliability, and it must be able to supply ever-changing load demand at all times. The dynamic changes of the load must be managed by the station so that there will be a continuity of delivery to the delivery of power to the end user. Power supplied should be of good quality. When I say the power quality comes down to quantum, what it is delivering, at what specified voltage it is delivering, and frequency as such, and its intermittency as such should be viewed. That we call as a power quality. Quantum, voltage, frequency, and its reliability or intermittency in delivery. If I consider the quality of delivery can be visualized. Then the power supply should be economical. This is the most concerned parameter from the energy side, because when you generate a power, somebody should be there to purchase it. So people will purchase if it is affordable or inevitable. So it should become so effective and cost effective. Everybody who is connected to that able to consume the power and pay for what they have consumed. So economic concern to the megawatt produced and megawatt dispensed for the end user should be very economical to be in transaction or business. It must satisfy necessary safety requirements. So it must be seen being engineering in aspect, whatever the investments and installations that has been taken and will be taken up to see to it that it adheres to the security, safety, and other concerned operational aspects of the system, which keep the system working for the present as well as for the future. When the people work on which, they should feel and ensure safety regarding that. And the power which we provide to the end user with at least two parameters if I observe. The system frequency must be kept at specified 50 or 60 hertz with a variation plus or minus 5%, whatever. And magnitude of the bus voltage to be maintained within a narrow prescribed limit. It should not have a much deviation in the terminal voltage. The generator is generating the voltage, delivering it to the grid. The terminal voltage should not vary to a greater extent, because we are very sure all the equipment, electrical equipment connected to the power system for one or the another activity from the load perspective also, they are very sensitive to the voltage. Any variation beyond the scope of its operation will definitely make the equipment to damage, if not malfunction, and deteriorate in its life. It means to say its voltage must be specified at a specified range only. So it must be maintained within it. That is an objective of the power system. Now that become an objective of the AGC also, because automatically you are trying to manage the requirement of the load and you are keeping the voltage as well as the frequency at steady state within the range. It become a task force for automatic generation controller to keep an eye on this all the time. Then we have seen some other things. The frequency variations are detrimental because it will affect the frequency dependent load, undue vibrations, increase of loss, turbulences, and they cause errors in digital equipment for their storage and retrieval. These are the concerned effects of frequency deviation. This we have already discussed in the another slide already, but again I have put it back. Why frequency is so important for power system operational control? Because I'll be discussing ALFC, automatic load frequency controller. Sensitive to the frequency, how is that controller try to regulate the flow of fuel to the turbine? We are trying to correlate. Hence, this becomes necessary for us to see the prerequisite. Frequency fluctuations are very important for us. The equipment which are interconnected and its adverse effects, if we know, there comes the need that frequency dependent things get affected and it must be controlled. Similarly, voltages are also detrimental for the equipment. This should be specified voltage, otherwise it will cause undue failure and result in havoc in the system. Therefore, it should be maintained well within the equipment range specified. So this would be the important aspect of AGC before it signal, and after being signaled to the set point, it should be kept in mind that deviations will not cross the prescribed ranges. Otherwise, these are the effects what one would find in the reality. It may be the corporation getting affected or the consumer getting affected, for which the result or reason is the deviation like this. Now coming to the generator side, it becomes very necessary for us to understand. So-called automatic generation controller, I am speaking, being a controller, computer control of energy generation and dispatch, it needs monitoring of voltage to the specified level. It needs to address the changes in frequency from the resource point of view. How that generation is worked out. So there could be one question, explain the basic control loops of generator with a suitable block diagram. So then this is the requirement. In order to perform voltage and frequency control in an energy control center, particularly a generating station, AGC, automatic generation controller, has to internally utilize two basic controls. One is automatic voltage regulator. which in turn look only for the management of terminal voltage constant, which will strive so that what is that required field voltage to the synchronous machine will be injected so that that field becomes strengthened enough to produce the required terminal voltage. That is the task assigned to automatic voltage regulator loop around the generator. The another control loop of a generator is automatic load frequency control. The keyword itself is very distinctive, automatic load frequency. As we are very much aware, any active power mismatch in the power system is reflected as the deviation in the frequency, because there is a strong interdependency of active power with the frequency. If active power is deficient or if the deficit, then its impact will be on the frequency. You will not be able to maintain the frequency at steady state specified. If frequency flicker, fluctuations are occurring, and it is an indicator that your actual megawatt balance is not happening, then it is the concern of this automatic control loop see to that load, active power what you draw, whose relationship on frequency is monitored and controlled. If there is a dip in the frequency, it is due to the active power demand not met appropriately. Suddenly, the deceleration of the generator has taken up or turbine has slowed down. Then immediately there should be a control action triggered to increase the input fuel to the turbine so that acceleration of the turbine takes place, so that such an acceleration at the generator side makes the megawatt suitable to the requirement. Once that acceleration takes place, the frequency of the output obtained superior to that. So in that way, frequency management is done. So in overall, the voltage control loop looks for a voltage betterment and managing, and automatic load frequency control look for the control of frequency as and when there is a change in load on the system. Then the first one, how we will visualize it? The automatic voltage regulator loop controls the magnitude of the terminal voltage. So the voltage of the generator is continuously sensed, monitored by a circuit. Then it is compared with a steady state requirement. Then the set point of a expected terminal voltage, actual value after sensing it is compared. If the comparison of set point and actual value on transformation become equal, it is to say set point is reached, terminal voltage is as expected. If there is a measured value is less than the required set point, what it indicates? Terminal voltage has fallen down. If that has fallen down, the upcoming control action is to control the field pole magnetization. Field pole supply properly, adjust it such that there is a shift in voltage in the next measurement. Like that, the actual set point of the required terminal voltage and measured line voltage from the generator using a circuitry compared. The comparison result may be both are equal, stimulus is 0, terminal voltage is as usual to continue. If the result line voltage is less than the set point, what it indicates? You need to control the excitation such that you will increase the terminal voltage so that it becomes required voltage. So stimulus is to increase the magnetization. Then another is, suppose the terminal voltage is very high than the requirement. Loads are suddenly removed from the power station. Suddenly voltage shoots up. Once the voltage shoots up, generator voltage regulator loop sends it very fast. Then it will automatically decrease that excitation control, so that on whose action the terminal voltage gradually comes back to the steady state. In this way, the management of terminal voltage to steady state value for its dynamic change, increase or decrease, is continuously monitored, controlled and acted on the excitation by this loop. We call it as automatic voltage regulator or automatic voltage controller. Both are same. Let us see the second one also. See here. These two are, this is a bigger block diagram. This I have taken from OI Elgard, a textbook called OI Elgard, an electrical energy system by OI Elgard. Similar diagrams are available in DP Kotari and Wood and Uhlenberg and other K. Umarao as well. Similar, need not be the exact and identical, but the concept what we find need to be similar. So this is one of the old fundamental book for electrical power system operation control from which it is being taken. Let us see what are the parts of this. So this is the complete part of the basic loops of generator. Now let me mark it one by one. Let us observe. Can you look at this? My cylindrical representation over here is a generator. This represents symbolically a generator. This generator is coupled to a turbine, rotating object. This turbine is driven by a prime mover, means turbine is having a fuel. This becomes a prime mover for the generator. Generator generates electrical power and pumps out. So, generator, turbine. For this generator, let us see, this generator on whose generation, it will take a transformer, line transformer and pump the power to the grid. So, three-phase power is pumped to the grid. From here, it goes to local load. This is the output side of the generator. For this generator to maintain the actual terminal voltage, this synchronous generator requires the magnetization of the field system. We call it as exciter. Exciter is a mechanism providing the field voltage, current, requirements of the main synchronous generator. This is a DC. I have shown a DC exciter. This DC exciter provides DC requirement of the poles of the system. Hence, on driving it at suitable RPM, generator generates the electrical power which you are coupling to the grid. So, this exciter is a part of the automatic voltage regulator. So, let us see before that, this exciter. For this exciter to control the voltage, whether to increase the voltage or decrease the voltage on the changes of the load, this has to respond to some stimulus. That stimulus is coming from measurement. You can see here, there is a measurement of actual power, rectification of that potential transformer. So we have a measure of voltage, potential transformer, and we are reducing it to DC or converting it to rectified DC. That DC is compared with the required set point, certain set point, certain V for this DC requirement here. That is compared with the actual value, comparator. And this error signal is amplified and fed to the exciter. If there is an error, stimulus, whether to increase or decrease. If there is no stimulus, what it is set is correct. So this part of the work, you can see this loop. This is a closed loop. This is a closed loop working on the generator field system. The field system is powered by an exciter. Exciter is a control loop, a system which provides a field requirement of the main synchronous machine, which in turn controlled by a loop, wherein the stimulus for this exciter is the signal from the comparator. This comparator takes a comparison of set point, standard required voltage equivalent set point, and what is the actual voltage measured through the sensors and transducers is compared. On comparison, there could be an error. This error signals the exciter after processing it and amplifying it, conditioning it properly. So, after having this error is signaled properly, conditioned properly, and it is connected to the exciter. Exciter now takes a correction whether to increase the excitation voltage or to decrease the excitation voltage or to maintain status quo of which. So that is looked by this entire loop that we categorize as, you can see AVR. You can see the flower bucket here. This right hand block of representation is called as automatic voltage regulator loop. This loop is responsible for managing the terminal voltage as specified by the energy control center. For this, independently, this loop is acting and functioning to see to it that exciter corrects its required feed supply to manage the terminal voltage as required. This comes the part of automatic voltage. I will magnify it and explain once again, no problem. I will come to the other side. Now I fall on turbine side. As you know, turbine may be anything, hydro-driven, gas or oil-fired, something like that. Whatever is the kind of raw material input you burn or turn into, this turbine is going to rotate or drive the generator. So this driving mechanism has to be sensed. You can see here, this is a control block, control valve. Valves need to be modulated appropriately, open, close, increase, decrease, or shut off. Whatever the kind of actions we initiate on this controlling of the valve, input fuel, either it is a water or a steam, will rush down to the turbine area. Turbine starts rotating. So turbine starts rotating on the action of the input fuel, and it starts rotating at certain regulated RPM. That regulation has to be done. Once there is a rotation of this turbine, I should have controlling of its RPM. Say certain 1000 RPM I would like to maintain. Such an 1000 RPM regulates its frequency as 50 Hz at the line power. Then the input flow has to be appropriately regulated in the control valve. Then you need to monitor the shaft speed. The shaft speed sensor is located at the shaft of this. It will pick up the RPM, N RPM. That will go to a speed governor. You will not worry about what is the left of this, right of this. Let us just monitor. Speed has to be measured. This speed has to be the input to the speed governor. There could be a control loop associated with the valve controller. This valve needs to be controlled by some controlling mechanism. That is done by governor and associated accessories. So, speed controlling is done in this loop which I am trying to boundary. This is the boundary which I am showing here. This is the boundary where speed control is done. This is called as primary ALFC, primary automatic load frequency controller loop. It means to say the primary objective of this rectangular block which I am highlighting is to see to it that the mechanical input to the turbine for your required speed is maintained properly. Hence, it is to correct the input fuel rate such that RPM what is to be maintained is regulated by the controller part of this. So, this is done by governor. Governor is less like an automobile. Automobile, when we accelerate through a pedal like a four-wheeler, automatically fuel injection system on that internal combustion engine and in the cylinder function to develop the power and to accelerate your vehicle or on whose reverse decelerate the mechanism. This is called a governor. Governor in this context is just to see to that actual speed is picked up. For this, some set point will be there. Some set point and what the actual RPM will be mixed up and error is developed. So, governor in this representation over here on a prescribed reference point, set point, like your example as automotive government services, if you imagine, there could be speed locking. Example, 60 km per hour. If you accelerate fullest length of the pedal, the maximum acceleration and speed what you can get is, suppose say 60 km per hour. That 60 km per hour is called as a limit set. It's called reference point mag. Like that, on this speed governor, there is some reference point riding from the previous control. That reference point and any error which is coming actually from the shaft of the turbine is combined, processed and develop a error that error will automatically amplified by the hydraulic actuator, hydraulic amplifier to control the valve open or close. We call it the gate control. It is not that easy. Manually, I can increase with the finger or decrease the finger. Huge mass and impact of work will be there on the turbine blades by this flow. Hence, operation of that valve, gate opening, closing in partial is not that easy. That is done by hydraulic mechanism. So, hydraulic amplifier is made to function on a requirement of a error by the governor. Governor checks actual set RPM, expected RPM. Are they same? No correction. Let it run as usual. If there is a dip in the RPM, the fuel input has to be increased. Then this speed and set point develop an error. That error is amplified and worked on this gate. Open the gate. Opening up of a gate makes higher the input fuel rate and turbine accelerates. Then the new value of speed is again sensed, error is checked, till the error becomes zero. There is an action of the governor to see to it that the valve is properly modulated, opened, closed, controlled. That we call it a modulation. Increase, decrease, manage it such that such an management make your required RPM and command what has been reached to the speed governor, and actual speed is used to compare it, and error is made zero. That is to say, this has to be steady state. This is the part of the primary automatic control loop, load frequency controller. This is not using frequency as an input. It uses speed as an input. The second is, now just see, who will set this reference for this governor? Somebody has to set it. So this we will see how this comes. This comes from previous block. How this previous block works? Let us see. After having primary objective of the control of speed of the turbine is done by a controlling loop, this generator is functioning and developing power and injecting to the grid. And there is a measurement of line frequency. You can see here, like how I measure the voltage for AVR. This frequency is measured by a frequency sensor. This frequency is used to sensitize a signal mixer. Here comes what exactly this generating station. I have taken only one generator. Likewise, suppose this is the only generator in a station supplying power to its neighbor and to its locality. There could be a flow of power outward here. This is measured. Power is measured and it is called as sideline power flow. What transaction this generating area is doing? That is sensed and its frequency is sensed, and it will transform power and frequency into area control error. This will transform the relationship of transaction, what it is doing, and frequency, what it is expected to maintain and what it is right now. That power and frequency were mixed as a signal mixer and it is transformed as an error. This error becomes area control error. This error has to be zero. Zero means what? There is no change in the command on governor. If this error is requiring some corrections, this will make the governor to open the valve, close the valve, set point. Set point change is done by secondary control. You can see this secondary ALFC. There is a flower bracket which is only for inner loop. This is the only loop. The outer loop is, you can see this flower bracket. This is complete turbine, frequency measurement, signal mixer, and all these things become secondary loop. Primary, secondary together become ALFC. So I am coming back to the fundamental discussion. Basic control loop are two: AVR loop, ALFC loop. ALFC loop is having two functions. One is primarily speed control, ALFC primary. Secondarily, it is a frequency dependent controlling to set point change. That is called secondary. So I was here. Who will set this set point? Set point is set by an authority. This set point changing is done by inner part or backward section here. This takes the measure of frequency and measure of exchange of power from the generating area, transform that as an error. This error will be integrated. So integrate such error over a period of time, accumulate them, and this in fact PID controller. Integral controller is a control system. When I go to next slide, you will see what is internal to this rectangular box. So this is called a PI or PID controller, which will process the error, integrate it, and overshoot of that error, aggregate it, and try to stabilize the error such that this error is integrated. Proportional to the error, there should be a change proportional. Integral to the derivative of the error, reduce its overshoot and bring the stability. That is being done on this error. That error is called as speed changer. Stimulus is speed. This is a request. This request makes a change on governor. Governor need to now act on shifting changes. So therefore, the integral controller on the power signal mixer works to request a change in speed by the speed changer. Speed changer accordingly make the correction to the governor. So input to the primary loop is a control output from the secondary loop. Secondary loop takes the frequency as the data, power transaction from the area, and develop an error. Error is appropriately nurtured. That is called as a speed changer request. That speed changer request becomes input to the governor. Governor accordingly change the control. Again, I will cut and show you the screen separately. Now you can see I have cut the only right part of that. Suppose you are supposed to understand only the AVR loop. What is AVR? Automatic voltage regulator loop. I have taken only generator. Turbine is driving the generator. Mechanical input. This is developing electrical power. So this is a synchronous machine and it's a field required input supply. So the field input supply is worked out by exciter. Exciter is normally a DC generator, DC machine which powers the requirement of a synchronous machine in an ancient concept. Presently, brushless exciters have come into real world. There is no separate DC. That particular concept is imbibed inside the generator itself, which acts as a rotating rectifier like concept. We call it as exciter. No matter, in a conceptual thinking of it, we require field poles of the synchronous machine be excited for its appropriate electromagnetic induction to occur. DC power supply has to be connected to that. That DC requirement of the field is processed and delivered by the exciter. So for this you connect and deliver it. To deliver and regulate, increase, decrease, that is done by a signal acting on this controller by a previous decision process, which is based on what is the actual output it is throwing out to the grid. Voltage is measured here because I am sensitizing it on automatic voltage regulation. What is the voltage required? What is right now? I want to compare and control. Then for its expected terminal voltage, I have a set point. V reference. V ref. This reference point I have set. On that reference point, the amplifier and the exciter responded to provide the requirement of DC to the field system. This generator developing the power. At what voltage? Line voltage. That line voltage is monitored through a potential transformer, PT, and rectified to a DC, and that DC value with a reference set point compared. On comparison, any error, if it develops, that error is processed, magnified, and applied to the exciter accordingly to increase or decrease the excitation so that line voltage is as expected from the machine. So that is the management of automatic voltage regulation connected to the synchronous generator. This comes under AGC. AGC has to take care of managing the voltage and managing the frequency. One part we discussed, that is assigned to a generator. Managing this activity is the role of AGC. So therefore, this has to be there on each generator. I am showing you one generator. Like that, there are 10 generators. You should have 10 such setups associated with each generator acting to the requirement commonly and as per requirement. This is about AVR separately. Similarly, I have ALFC, second part of which I have clipped it. You can see here, I have a turbine, I have a generator. Then you can see my primary loop. Primary loop of ALFC, automatic load frequency control. This is very clear. As the load changes, frequency gets affected. That's called automatically load changes, frequency and controlling it. It means this loop is acting on dependent on frequency. So that has to be in this regard, primary and secondary, and together it is a ALFC. So therefore, we call it as primary and secondary. There could be one good question on this. Explain ALFC with its function. So further we will see what are all the internal parts of this rectangle box by control system. We have to see. We are at the very initial understanding of basic loops. Hence, for me it is very easy. Let us understand constituents of this loop, which is a generator which is coupled to a turbine and turbine RPM, because my requirement is a steady frequency. Expected frequency I am monitoring by two ways. One is RPM of that I am monitoring, frequency of that I am monitoring. It means frequency of line power. Therefore, when I monitor speed to a governor governs the valves such that input fuel to the turbine is regulated according to the contingent speed variations at the turbine. It is expected to run at say 1500 example. It should be 1500 plus or minus the tolerance is expected. If it is going down, what is the purpose then? Immediately valve have to open to make the higher input fuel, make the turbine to accelerate. That is the decision taken by the governor. Governor in turn, after having its set point, maintaining set point fixed, then actual speed is taken. Comparison of these two to process the need for the opening or closing of the valve is done by the governor. Separately, I have a one centrifugal governor, fly ball governor. We will show you in another slide. So therefore, this governor on the act of pre-required attainment, actual RPM, on whose comparison governor process developed an error. So displacement error and control error, that is amplified to by an hydraulic amplifier. Hydraulic amplifier using the flow of oil, solenoid and blocks. It will work on the control valve so that valves are regulated so that input fuel to the turbine is managed. Once the management occurs, RPM picks up. This is the primary part. You may ask me, having it done, can you ensure the frequency of the line constant F? Definitely no. If I do not monitor the frequency here, simply work only with the primary part. Can it meet my requirement? Definitely no. This is called mechanical supplement to the electrical load. As the load changes, frequency falls. Frequency falls means RPM has diminished. That you are correcting by controlling the input fuel. That will not be, this will not be measuring the frequency, measuring the RPM in fact. Therefore, there should be another superior controller associated with it, which will take care of actual line frequency itself. Line frequency with the frequency sensor, once it is measured, that will be mixed in the signal mixer, which is taking care of what is that power transaction that this generating area is doing. We call it as sideline power. What is that exact exchange this generating area is doing with its area neighbors? That is being taken as input, feed as a frequency, and transform this into a control error, area control error. This control error need to be 0 all the time. If it is 0, the meaning of which is the set point of governor and what the wall it has opened, what is the frequency it is reached here, what is the RPM available here or at steady state. That's the indication that system is in steady state. But electrical power system which experience turbulences, dynamic changes in the load, definitely be all the time alert, actively participating in the control. Therefore, we cannot say it is safe right now. Contingent changes have to be automatically taken care and act on the error and see to it that this error is processed by PI controller and its control outputs are changing the speed settings on the governor. So this speed changer is nothing but set point. Suppose it was having in terms of delta P ref. It means there is a diminish of megawatt even after having its set point set. Increase, it is not able to cope up. Then this set point has reached maximum. Then this set point needs to be revised. Revision of set point of the governor is done by signal mixer, PI controller and speed changer action. This part is going to supervise action on need for the change of set point of the speed governor. The speed governor in turn acts individually till that point. If it is able to achieve it, well done. If it is stalling there only, not able to achieve it, then it is a need for secondary control to supervise and change the set point such that relaxation is given to this controller to increase further input to the turbine. It may bring your requirement. In this way, governor's set point is done by speed changer mechanism. This speed changer will change the speed, modify the set point only after having signal mixer and understanding the error of this locality as called as ACE. ACE being brought to 0, whatever is the output available, that output makes the speed changer to respond positively to increase the set point or to decrease the set point. Later it will not act. That will be only the governor acting on that. So primary loop is continuously operating on the set point. Set point modification is done by secondary loop on observation of sudden change in frequency or drop in frequency with respect to power flow, what it is doing on the neighbor. This way, ALFC loop with primary loop, secondary loop function in the energy control center generating station. It is on a generator I'm speaking. So primary loop, secondary loop, together ALFC and AVR independently. Now comes the question. How is that ALFC, AVR together function? Yes, you see this is the entire interconnected generating area where you have primary, secondary loops of ALFC, AVR loop. So these two are working hand in hand. The automatic generation controller concerned to generation aspect has to look after managing the terminal voltage, look after AVR, manage the actual megawatt delivery, balance it for a contingent changes in the load from variation what you notice from frequency perspective. Manage it, actual megawatt is managed. Manage this voltage, terminal voltage is maintained. So this has to be sync. ALFC, AVR have to work hand in hand together so that there is a proper balance of generation of active and reactive power at certain specified voltage keeping the frequency at steady state desired. That is the role of basic control loops under the AGC, automatic generation controller, will supervise these things at generators. So therefore, you can imagine a generating station. There are 5 generators. Let us imagine there itself a computer room. That computer room monitors all the 5 generators. Each generator is having its connection with the computer. Computer is appropriately addressing AVR, ALFC loops of each generator. Then that AGC, automatic generation controller, concerned to a generating plant, becomes AGC local. Now, such a AGC connected to neighbor corporation. Imagine there is another B generator station which have 10 generators. Imagine there is a computing facility which control all the 10 generators and deliver the power to its load. And that AGC of plant B, AGC of plant A can interconnect themselves for the proper trading of power. That is called as AGC interconnected from area 1 to area 2. So locally they can generate themselves in their area and deliver. They can look for somebody's need on requirement. And these areas, A with the AGC local, B with the AGC local, get connected to master terminal unit, which is at the energy control center, central to the total energy system, which will supervise all the generators at all the time of observation. That's called as integrated. So that is how that central controller, national, regional and state, like that we can simulate. In the next slide, upcoming slides, I do have such interconnection. What is the meaning of that? Like that. Let us focus. How is that AGC viewed from simple one generating station perspective, connected to such neighbor generating station, connected to central energy control center, like that. These were the slides which we can understand from this. The next slide itself is there are some definition. So after this I will stop. So commonly used terms related to automatic generation controller. It becomes necessary for me, without discussing these things further, interaction becomes very difficult. So the first keyword connected to the automatic generation controller is control area. Let's see. I have just pushed it. See, it's an area. It is an geographical encompassed boundary, which is a power system or a part of power system, which is having generator, load, controller, etc. like that. You can see the dotted line. It is not in a proper shape. Whatever is the shape available, this is the geographical periphery being supervised, controlled by a single energy control center. Automatic generation controller, computing facility, managing generation and dispatch of power, controlling it. Its signals are sent. Signals can reach up to this point P3, P1, P2, P4 like that. These are the corners or bus terminals from which exchange of power is being taken. You can just, the dotted line shows this is a reason. Control area is a reason. It is a part of the power system or a power system. Till that boundary, common control signal reach from the generating controller. Automatic generating controller signal increase the generation, decrease the generation, isolate the load. Something common control signals are emitted from this automatic generation controller. They will reach this periphery. That's all. Outward to this, these signals are not reaching. Like a mobile tower. Mobile tower will have its radiation or its communication as a base station to the circle. Later hit signals of that station are not available. It will be some other station like that. Like that, control area is a area, geographical periphery or a part of power system or a power system. Till that periphery, common signal, common controller signal will reach. Control signals from the computing processor will reach and control. This we call as control area. Area under the control of a control generator or automatic generation controller can be supervised, managed, which is geographically spread around that. Outward to that, it has no action, not responding. This is the first area definition, control area. Area till that point, common control signal from a computing controller reach and exchange. That's enough. So therefore, the next aspect is tie lines. And what are tie lines? Tie lines are the transmission infrastructure. Transmission infrastructure laid to exchange the power from one generating corporation or a one control area to the neighbor. Suppose, imagine this is a energy control center, control area. Till this point, dotted line, control signal reach and control this operation, boundary. At the boundary, I have marked here something cross, P3, P1, P2, P4. These are the terminals from which exchange of power from this corporation to the neighbor or from the neighbor to this corporation happen. So these are called transaction points. So P1, there is a transaction of power from this point to the next corporation, either to sell or borrow the power. There is a measurement taking place here. P1 is a measurement. P3 is a measurement. P2 is a measurement. P4 measurement. So from this point and later till the next corporation, transmission lines run. Those transmission lines we call as a tie lines. Tie lines are the transmission infrastructure connecting control area with another control area, like this. You can see control area I, control area K, control area J. So they have a transmission lines. These are called as tie lines. Tie lines are the transmission lines connected between control areas for exchange of power, nothing but power trading, to buy or to purchase the power on the need for their appropriate management of the power system. So this is how tie lines are the facilitators. What is the difference between an ordinary line and tie line? They are the physical transmission lines only. They are called tie line because they are meant to exchange the power between the corporations of type 1, type 2 or another in business. Then next keyword is net interchange. Let's see what it is. Net interchange is power flow in or out from a area. Suppose area A is having certain generator, the power flow from that is power in or out, net exchange. If the positive value indicates flowing out, negative value indicates inflow. It means it is just like an account. What is that exact megawatt the area is handling? If there is a power with the value, net interchange value is having a plus edge of it, it indicates surplus generation is there. Power is surely flowing out of the control area to the neighbor. If the net interchange value is leading with a negative sign, that value of megawatt indicates it is being borrowed from the neighbor corporation, like that. So net interchange, the word interchange says transaction from the control area to the next control area only between multiple corporations. Plus indicates the current area that you are speaking is having excess generation. Minus indicates it is a deficit generation, like that. Next definition is frequency. There are multiple frequencies labeled: system frequency, standard frequency, rated frequency, scheduled frequency, frequency bias. So many connected frequency relevant terms. Let us see one by one. When I speak about frequency, the system frequency refers to actual frequency of the system AC voltage. See a small difference in keywords from one to one you can notice. System frequency refers to actual frequency of the system AC voltage in practical terms. Actually what I am finding, it is the AC voltage frequency, system frequency. Look into the keyword standard frequency. It is the frequency intended to be reference. It is the standard frequency. Nothing but frequency intended to be reference. Let's say 50. 50 is the standard frequency. If the frequency achieved also 50, system frequency is same as standard frequency. Like that. Standard frequency refers to you are setting it as your requirement. Intended frequency as a reference. Like that. Now come to the next one. Rated frequency. See a small change. Frequency of equipment for which they are designed. Like an example, you have purchased some measuring devices from USA to your Indian perspective. Before getting the 50 Hz set point on that, wrongly you have not changed the frequency to 50, you are 60 running. Then definitely the 60 Hz based designed inside operational controller will definitely respond for that. The frequency right now in the continent where you are installing is 50 Hz, internal setting is 60 in that component. Definitely that system once installed might project wrong things. Protrude errors into the system, erroneously it may function. In that regard, rated frequency refers to the individual component for which they are designed and they are able to work in sync with the actual frequency. So this must be noticed for the component that you are going to integrate into a system. Therefore, rated frequency refers to the frequency of the equipment for which they are designed. So this is very much important for digital instruments and all, wherein the carrier wave, the frequency of the signal and its control, all those things are concerned to that. Not only that, even our conventional equipment as such. The next keyword refers to scheduled frequency. It is the frequency that the system attempts to maintain. Here, standard frequency is a reference intended. System frequency is the frequency actually possessed. Scheduled frequency is the frequency attempted. So when I say 50 Hz, can they be altogether closer to 50 only? Yes, they must be. Scheduled frequency refers to the frequency that the system attempts to maintain. It may happen 50 Hz is your requirement. Sometimes it becomes very difficult to control the primary loop of ALFC by changing the mechanical input to that. RPM is not raised up. Then the scheduled frequency at that time, it attempts to settle to 49 Hz only, 49.5 Hz only. That time, your standard frequency stands 50, actual frequency stands 49.5 or 49, which is system frequency and scheduled frequency there only. In this due regard, a frequency from a small narrow width of control can be categorized as these many by definition. It is the frequency that the system attempts to maintain. For me, it should be 50. It should be 50. Standard must be 50. System frequency must be 50. And rated frequency of all the components must be 50 in continent what I am speaking. So therefore, all these are the one another form of frequencies concerned to the operation and the equipment in the function. The another keyword is frequency bias. Just see the keyword frequency bias. It is a required offset in the scheduled net exchange of power from a control area. Now here comes the concept of why frequency changes occur whenever there is a change in megawatt power. Yes. Who will act on this controlling? That is what the stimulus we are going to get from this frequency bias. Frequency bias is the net set point change at the generator for a drop of frequency due to rise of load on the station. It means to say, we have a very particular relationship of active power with the frequency in the power system, dependency of frequency and active power. Frequency will fall preferably when there is a load increase in megawatt. If there is a megawatt change, increase is noticed, then definitely a change in frequency lower side is ensured. That frequency, if you are not shifting back to a steady state, which is diminished by a small 0.5 hertz, 50 to 0.5 hertz down state, if you are not increasing it back to 0.5 hertz and 50 maintaining, that megawatt you cannot fulfill. That further increase of load will make the frequency to diminish further and further. That drop of frequency due to megawatt is called as the offset, the correction required to generate electrical power, which has really resulted this dip in frequency. At the point change in megawatt, what will definitely shift the frequency back to steady state is called frequency bias. Though in other terms, frequency bias is a necessary change in megawatt set point on the generator to set back the frequency error back to zero. So dip in frequency has to be brought back to steady state. Dip in frequency has to be brought back to steady state frequency. To bring it back, what has to be counteracted? It has to be counteracted on the active power increment. That megawatt shift adjustment, what I have to take, that's called shift in offset, required offset to increase the generation so that fall in the frequency is counteracted. That is called as frequency bias. In the next few classes later, I will be using the keyword area frequency bias. Why a certain area experience a drop in frequency? Who is responsible to act on this drop of frequency? All such terms surely we will understand in the later part. While before reaching them, let us understand the meaning of frequency bias. It is the necessary offset in megawatt set point at the generator to cope up drop in frequency back to the steady state. That's the one. Next we have time deviation and load frequency characteristics, station control error and unit control error. So these are three more points. Let us put some light on this and we'll make it final. Time deviation, the ratio of accumulated difference, the system frequency between the system frequency and rated frequency to the rated frequency. It means the ratio of accumulated difference between the system frequency and rated frequency. There is a one keyword extra has come, we will eliminate it. So it is the error. We have to find out what is the frequency right now, what is the expected rated frequency. The next time, moment of time, observe what is the actual frequency, what was expected rated frequency. Those accumulated deviations, if you take a ratio, that's called as ratio of accumulated difference between actual frequency system with the rated frequency in the numerator to the denominator rated frequency. So this, if I take, that becomes time deviation. This is required. So how long the system is taking to cope up with deviations in frequency in observation. That is noticed from time deviation parameter. This is the ratio of changes, accumulated difference between system frequency and rated frequency. Error, rated actual in the numerator. To which in the denominator, rated frequency has to be taken. So that gives you time deviation. Load frequency characteristics. A plot of load of a control area to the frequency. This is one of the very important characteristics in the generating station dispatcher need to understand. It is a plot of load and frequency. How is that frequency of that station changes as the load changes? Plot of load on the station and the frequency of that station. Naturally, frequency need to be steady state at specified value f, whatever the reference. But due to the changes in the load, as the load changes, its impact is to affect the frequency deviation do occur. How is that? What is that deviation? You will find at the station as the load changes is a graphical representation. That's called as a plot of load of a control area to the frequency of that station. This is called as load frequency curve. Again, we have generator and frequency curve. Generator output, generated megawatt with respect to frequency of that output of the generator. How is that certain generator change its generation as the frequency changes, or expected to change its generation as the frequency changes when a command is given to that? That becomes a characteristic of a generator. Like a load frequency characteristics pertain to a station. As the load changes, impact of that with the frequency we are measuring. Similarly, generator perspective, generation and its frequency we can consider. Then we have station control error. Station control error, this is the difference between station generation and assigned generation. If certain station is assigned with so much of X megawatt, but output what right now is giving you Y megawatt, then the difference between these two is called as station control error. It is to be zero. What it is given, it must be generated ideally. Due to so many contingent parameters playing on the power system control, there could be a riding hand and there could be a small following error with this. That we call as a station control error. Difference between station's actual generation and expected assigned generation. Unit control error. When you come to a single unit, it is the generation from a unit minus the assigned generation of a unit. When I come to a generator in a perspective, so much of 10 megawatt, 9 megawatt, 25 megawatt, like that. Expected and actual generation. What is right now happening with respect to each unit, magnified view of it, is called unit control error. Likewise, these are the few keywords connected to automatic generation controller. I just go back here, I just review it once. This was the area we were discussing, control area. Then we came to tie line, we came to net exchange concept, we came to different definitions of frequency, we came to some other definitions of this. So this is how a basic definition we have come to know. So in the next class, we go ahead with the further discussions and view of this. Okay. Meantime, I will just view the total attendance and I will come back. Okay? Please wait for me. So there are 30 members on my account. I will just record their attendance on 30. Okay. So I will just stop presentation. Thank you. Thank you one and all.